As we push into the era of large language models, we hit a physical ceiling. Throwing more compute at the problem eventually stops working. To understand why, look at the baseline architecture, the standard dense transformer block, specifically models like T5. This diagram shows the feed-forward network, or FFN. In a dense architecture, every single token in a sequence must pass through this exact network. Because of that structural requirement, the model's total parameter size and its per-token compute, measured in flops, are permanently changed together. This creates the dense scaling wall. When engineers increase the size of the FFN to hold more parameters, the compute cost for every single token increases proportionally. You cannot scale up the memory without paying a massive tax in active math. This creates a severe engineering bottleneck. Scaling a model to 1 trillion parameters is economically impossible if every forward pass requires 1 trillion parameters worth of active computation for every single token. In 2021, a team led by William Fedus designed a way around this bottleneck with the Switch transformer. Their architecture introduces a concept called simple and efficient sparsity. It acts as a mechanical lever to break the one-to-one lock between total parameter count and per-token execution. To build a 1 trillion parameter model, the architecture itself has to change. We have to design a system that can grow massively in memory storage, while keeping the active per-token compute roughly flat. The Switch transformer makes a highly specific surgical edit to the standard block. The multi-head self-attention layer, the part of the network that handles context, is left entirely untouched. It remains dense. Instead, the dense FFN sublayer is replaced in alternating layers. The single dense FFN becomes a Switch FFN layer with a top-1 router and n independent experts. When a token enters, the router generates a softmax probability distribution across all available experts. In classic mixture of experts routing, the network sends each token to the top 2 experts. Switch transformers use top-1 routing. The router sends each token to exactly 1 expert, snapping to the single highest probability match, leaving the other expert lanes completely dark. Sending tokens to a single expert creates 3 compounding engineering wins. First, it drastically reduces the computational overhead inside the router itself. Second, it requires smaller capacity buffers on the hardware, since each token only occupies memory in 1 expert rather than 2. Third, it yields a significantly smaller all-to-all communication volume across devices. A single destination means half the network traffic. The router's confidence probability still plays a critical role. This decimal acts as a gate value. The chosen expert processes the token, and its output is multiplied by this gate value, ensuring that low-confidence routing attenuates the final signal. Top-1 routing strips away the complexity of traditional mixture of experts, making massive sparsity practical to execute across thousands of chips without collapsing into a communication nightmare. Software routing is highly dynamic, but accelerator hardware is completely rigid. TPU and GPU compilers demand statically shaped tensors at compile time. An expert cannot have a dynamically resizing memory buffer to accommodate a variable number of tokens. The tensor size must be fixed. Switch bridges this gap with a strict expert capacity rule. Total batch tokens divided by n experts, multiplied by a capacity factor. A 40-token batch across 4 experts means a 10-token limit per expert. If routing skews, 12 tokens attempt to enter expert 0. The hardware cannot simply expand to accept those extra 2 tokens. This triggers the overflow mechanism. Expert 0 fills its buffer first come, first served. The 2 rejected tokens bounce off and bypass the expert boxes entirely via a parallel residual connection path. A common engineering misconception is that these dropped tokens are permanently deleted from the model's memory. They are not. They are only dropped for that specific feed-forward layer. The dropped tokens representation passes entirely unaltered to the next transformer block, carried safely forward by the residual path. At the end of the sublayer, the process tokens, scaled by their gate values, are merged back together with the unaltered dropped tokens before the final layer norm. Strict capacity limits and residual bypasses are the critical bridge. They force highly variable, data-dependent routing software to run efficiently on completely inflexible static hardware. To save memory and network bandwidth, the vast majority of the Switch transformer executes its math in bfloat16, a computationally cheap floating point format. The problem with bfloat16 is that while it has a wide dynamic range, it has very low mantissa precision. That lack of precision mathematically breaks the softmax operation inside the router. A broken softmax creates a corrupted probability distribution. Tokens are sent to the wrong experts, completely ruining the model's ability to balance computational load. This flowchart illustrates the architectural fix, a precise numerical seam. The nodes highlighted in red, the linear projection and the softmax, operate entirely in 32-bit floating point. The surrounding pipelines run in bfloat16. The higher precision FP32 is surgically isolated only to the router's local projection and softmax to maintain numerical stability. Once calculated, the resulting dispatch tensors are cast back down to bfloat16 immediately before entering the bandwidth-heavy all-to-all communication network. This chart demonstrates a massive behavioral problem inherent to Top-1 routing. Left entirely to its own devices, the network will inherently learn to route almost all of its tokens to one or two favorite experts. Those favorite experts immediately hit strict capacity limits. Millions of tokens drop, while the remaining N-1 experts receive no gradient and effectively die. To stop this collapse, an auxiliary load balancing loss is applied. This mathematical penalty pushes the utilization lines toward a uniform horizontal average. By adding this auxiliary loss to the main task loss, the system heavily penalizes uneven routing. It forces the optimizer to distribute the tokens evenly, targeting a 1/n distribution across all available experts. By isolating 32-bit precision for the softmax calculation and applying an auxiliary loss to protect token distribution, the Top-1 architecture is stable enough to scale. Look at this macro-level view of a massive switch transformer stack. As a single token passes through the system, only one expert node actively lights up per layer. The rest remain entirely dark. This visualizes the decoupling lever. Because only one expert executes per token, engineers can simply increase the total number of experts, N, to scale the parameter count without triggering the dense scaling wall. For any given token passing through the network, 99% of the model's parameters are strictly stored in memory, not executed in active compute. According to the original scaling results, this architecture allows the model to reach 1 trillion parameters while keeping its active per token flops roughly equivalent to a vastly smaller dense model. But while pre-training a sparse model of this size is highly efficient, attempting to serve a trillion parameter sparse model in production is a logistical nightmare. The sheer memory overhead required to store thousands of idle experts, combined with the latency of all-to-all routing at every single inference request, makes serving it economically unviable. This diagram illustrates the final phase of the switch framework, knowledge distillation. The massive sparse architecture acts as a funnel, projecting its outputs into a comparatively tiny, streamlined dense student. The massive sparse model is essentially a pre-training asset. It acts entirely as a teacher, explicitly meant to train a much smaller dense model. The dense student is trained to match the teacher's exact output distribution on the same data. It inherits the complex intelligence that the sparse model was able to acquire cheaply during pre-training. When it comes time for deployment, the complex router, the massive array of experts, and the rigid capacity logic are all completely discarded. Only the lightweight, dense student model is actually served to users. The entire system rests on 3 distinct pillars. Top-1 routing decouples scale from compute. Capacity limits bridge software to hardware. Distillation bridges pre-training to lightweight production. Massive sparsity is not necessarily the future of inference. It is the ultimate pre-training lever, a highly specialized structural hack to buy massive scale for cheap before throwing the scaffolding away.